So this here is a differential equation, okay? And it's called a Legendre differential equation for the reason I'll show you in a second. Now, when we attempt, are you connected?
Yeah, I just clicked the thing. It's connecting.
So,
and I'm connected.
Okay, so this is a second order differential equation here. Okay? This here is a second order. I just want to explain to you, like, to make sense of these Legendre polynomials, what they are, okay? So this is this is kind of what this is all about. This is the differential equation, okay? This is a second order differential equation. Okay, so now if you need to solve it, there's many ways to solve this. One of them is using the series method, sort of what we did on problems 1 and 9 from section 1. We assume a solution of a power series form, differentiate, plug into the equation, do all this good stuff, and then figure out a recursion relationship between the coefficients. So this is the steps that go in the middle. This takes you to this recursion relationship here. an plus 2 equal an, etc. Okay, now you take this and you plug it back into the original assumed differential equation, and you get the solution for the differential equation, which is made up of two different series. The first part, which is the x4, x6, etc., and their coefficients, and the odd polynomials, x, x cubed, x5, x7, etc., with their coefficients. Now, it would make sense that since this is a second order differential equation, you know that you have two unknowns in this equation that need to be evaluated using either initial conditions or boundary conditions. Aside from that, you don't know what those are, and these are we call them a0 and a1. And the point is to express, the point of this recursion formula is to express all the remaining coefficients. There are n coefficients in the solution, is to express these remaining coefficients in terms of a0 and a1. Okay, so once you do all the steps needed in between, it turns out that y is made up of two series. One multiplies a0, one multiplies a1. The a01 carries the even powers of x, and the a1 carries the odd powers of x. Now, if you were to apply the ratio test, okay, you would see that this series converges, okay, for x squared less than 1. And for they do not converge, okay, they diverge for x squared equal 1. Okay, we're not going to do the ratio test. This is old news calculus. You know, you could apply it, and I'm just telling you the results. I've done separate videos on convergent and divergent series for those people who would like to know how to apply on ratio test in general, how to apply the ratio test to a series. Okay, now let's take a look at the a1 series, which is the one carrying the odd. So there's two series here. There's the let's call them the a0 series. Okay. This is the a0 series times a1 times a0, and this here is the a1 series times the a1. Okay, so if we look at the a1 series, and then let's take L equals 0. Okay, now assuming that x squared equal 1, okay, so I'm looking at the a1 series, L equals 0, what would you get? Plug it in, you would get 1 1 because you get 2 over 3 factorial. So yeah, so you would get 1 plus 1/3 plus 1/5 plus etc. Okay, now if you were to apply the integral test on this diverges. So the A1 series for L equals 0 diverges. Okay, now why is that important? That's important because in many applications we will take x to equal cosine theta. Okay, and we know that this is going to be between -1 and 1 because cosine theta is in between -1 and 1. Okay, so the point is we want a solution that converges for all x, for all theta. Okay, for all theta, that means we need a solution which converges at the bounds at plus or minus 1 and in between. Okay, and you could always find one but not two solutions where L is an integer. Okay, let me explain, and this is where the Legendre polynomials come in. So for example, when L was 0, right, we looked at the A1 series and we said that it diverges, correct? That's for L equals 0. Okay, A1 series. Now let's look at the A0 series. Well, the A0 series, if you plug in L equals 0, you see that you're gonna get y equal A0 because all the remaining terms have L, and if L is 0, they all go away. Okay, so you get y equal A0. Okay, now if L equal 1, okay, if L equal 1, let's actually let's do it like this. So for L equals 0, so for L equals 0, A0 series, we get y equal A0, and the A1 series converges. Okay, let's do it in a tree format. It's easier to see it. Now, for L equal 1, right? If we look at the A0 series, now if you plug 1 in the A0 series, you get L times L plus 1, L times L plus 1, so those terms are increasing, and you could apply either test there, right? You could apply either test and find out that the series diverges, right?
You disappeared for a minute there.
I did? Okay, I was saying, so I'm taking different values of L now, and I'm looking at the A0 series and the A1 series separately. Okay, I'm trying to show you that every time you pick an integer, one of the series will diverge and the other one will converge. Okay, so for example, when L is 0, A1 series converges, diverges. Okay, and you get the A0 series y equal A0. Okay, so this guy diverges, the A1 series diverges for L equals 0. Okay, but you get the A0 series. Now if L equal 1, then the A0 is divergent, so A0 series diverges, and you can easily test it. Okay, and let's look at the A1 series for L equal 1. a1. Now notice that when L equal 1, the only term that survives is the first term, because every factor has an L minus 1 and those will all go to 0. So we get y equal a1x. Okay, so the opposite happened here. The A series diverges and the A1 series converges to A1, right? So if you were to take any integral L, right, one series will terminate giving a polynomial, the other series will diverge at x squared equals 1. By the way, negative values of L would give the same solutions obtained for the positive values of L. Okay, so that's why we keep those L's positive numbers. Okay, so hence when you do L equal 2 and L equal 3, etc., etc., okay, every time one series will converge, one series will diverge, and as a result you get a set of polynomial solutions of the Legendre equations. For each for each positive integral of L, you get a polynomial, okay, and each one of these polynomials will have an arbitrary constant, a0 if the a0 series converges, and a1 if the a1 series converges, right? So for example, for the L equals 0, the y was a0. For L equal 1, the y was a1x, and so on and so forth. So so now if you were
Let me plug my computer in. Hold on 1 second.
Okay, so if the value of a0 or a1 in each polynomial is, if you select it such that we get, yeah, so I was saying, so for L equals 0, one of them converge, the other diverge. For L equal 1, vice versa. Let's just take L equal 2 just for illustration, and see what happens. So for L equal 2, notice if you look at the terms, you're gonna get L minus 2 on the a0 series, so those will all go away past the x squared, and if L is 2, you will get 3 times 2, 6 over 2, 3x squared, so 3x squared. So a0, so the a0 series will be a0 1 minus 3x squared, right, if L is 2. Okay, and all the rest will cancel out, and the a1 series, so this was the a0, and a1 series, the a1 series will diverge. Okay, and so on. If I were to continue 3, 4, 5, 6, so those polynomials that I'm getting from those integer values of L equals 0, L equal 1, L equal 2, etc., etc., where one of those series is convergent. So for L equals 0, y equal y0. For L equal 1, it's y equal a1x. For L equal 2, it's a0 1 minus 3x squared. Those polynomials are called Legendre polynomials. Why? Because they are selected so that when x equal 1, y equal 1. So for example, if y equal 1, plug this in here, that immediately tells you that y equal a0, y equal 1, right? Y equal y equal 1. If y equal 1, that means a0 equal 1, and therefore y equal 1. This here, y equal 1, is the 0th Legendre polynomial. This is called p0 of x equal 1. That's what the question is asking you to do, to figure these out from the analysis of these two formulas. Now, if I go, let me go to L equal 1 and get the next one, the P1. So this is the first one. Now I go here, right? So when x equal 1, y equal 1, so I get 1 equal a1 times 1. So a1 equal 1, and I plug that back in, so I get y equal x. This y equal x is the first Legendre polynomial. It's of degree 1. Okay, so this is p1 of x equal x. This is a Legendre polynomial p1 of x. Now if I go to L equal 2 and do the same exact thing. So for L equal 2, I will consider this. And again, I will set x equal 1, y equal 1. Right? So I get 1 equal a0 into 1 minus 3 times 1 squared. So I get a0 equal this is what's this, 1 minus 3 is minus 2, minus half, right? And if I plug this in, I will get y equal minus half into 1 minus 3x squared, and if I switch this around, I get, this is my third Legendre, my second, well, if you're counting p0 as the first, this would be the third Legendre polynomial, p2 of x equal 1/2 3x squared minus 1. So these polynomials I'm finding are called Legendre polynomials, and they are a result of the series solution of the differential equation we started with, and that's why that differential equation is called the Legendre differential equation, because the solution, the coefficients for the solutions that we obtain generate these Legendre polynomials when you take all the values, the integer values of L, from 0 up to whatever. Okay, so this is what you're doing in that question. For instance, let's just extend this explanation one step. Let's say I want to see how it works. Let's say, so I did L equal 1, L equal 0, L equal 1, L equal 2, yeah? Let's say you want L equal 3. L equal 3. So L equal 3, right? L equal 3. L equal 3, if I go to the series, notice that the A1 series, starting on the third term, you have L minus 3. So every term starting with the x5 term and beyond will be zeros, and the only one you will be left with is the first two terms, x and x cubed. Okay, so with the A1 series, you will get y equal A1 into x minus So x minus, okay, let's plug in the 3 now. So 3 would get us 3 plus 2, 5, 3 minus 1, 2, so 10 over 6, which is 5/3 x cubed. 5/3 x cubed. And then the rest will be zeros because they all have a factor of L minus 3. Whereas the A0 series, if you look carefully, if L equals 3, you can test that, the numerator starts getting larger and the A0 series converges. Diverges. Okay, if L equals 3. And so this part here diverges. And you could easily test it. Okay, so this is my, so now I could say, okay, then I go here and I solve for A1 using x equal 1, y equal 1 and plug it in. So you get 1 equal A1 into 1 minus 5/3, right? So 1, what's this, 3 minus 2/3 A1, which makes A1 minus 3/2. And then plug it back in, right? And so that gets you the P3 of x. So the next Legendre polynomial, P3 of x, is, if you FOIL this, you will get 5/2 x squared minus 3/2 x. And you know, you could continue and get all of them this way. Sorry, this is x cubed, I meant, not x squared. So this would be P3 of x. P3x, Legendre polynomial.